appreciate your patience. So this is the last slot today, and I do my best to release you as soon as possible to the hard day's night, right? But I have a lot of stuff to report, so let's not lose too much time. Allow me a remark on the history of this paper. It was about one year, a little bit more, when Samuel Forrest and myself finished a paper which is thermomechanics of gradient plasticity, but that was restricted to small deformations. So at the time, Samuel would say to me, why don't you expand this to large deformations, because there is still a format, a general framework missing. There are a number of approaches, but what is really needed is a general scheme or a general framework for that. And since Samuel knows the literature much better than I do, well, although I read a lot, I took over this challenging task, and today I can present the results of that. So you see, there is a reasonable list of approaches which take into account large deformations and gradients, and there are sure many people in the auditory which I did not list up here, so I apologize for that. But still, a general framework is not among them. So if you try to enlarge such a theory to finer deformations and, in fact, large temperature changes, immediately certain questions arise. One of the questions is, for example, which are appropriate variables in such a context to not get into conflict with invariance requirements. But also one wants to know what are reduced forms then, which are identically fulfill these invariance requirements. You want to know what symmetry transformations are. You want to define what would be an isotropic material or an anisotropic one, what is a fluid and what is a solid, etc. So all these questions need some answer. And if you leave the ground of elasticity and go over to plasticity, even more questions arise. What about decomposition? Which variables have to be decomposed in which form? Multiplicatively or additively or what else? So all these questions arise and will be addressed during this talk. And if you go into the scope of thermodynamics, then immediately the question comes, how can we fulfill the second law? Okay. Just some references. The paper I just mentioned within small deformation is this one, already appeared, and the thermodynamics, the thermodynamical ground is based on this paper, and the finite deformation theory is perhaps a follow-up of this paper by Samuel Forrest and Rainer Sievert, late Rainer Sievert, and I did my best to continue in the spirit of this first paper. Now this is the content of my talk. The starting point is a stress power, and then we go over to second gradient elasticity, and since I prefer material variables to not go into conflict with Euclidean invariance requirements, these all depend on the choice of the reference placement. So we have to investigate change of reference placement. And after that leads immediately to the question of isomorphism. If you want to give a precise answer to the question whether 2 points reflect the same behavior. And if you apply an isomorphism to the point itself. It's an automorphism or a symmetry transformation. So that will be the third chapter within the elasticity. And then we go over to gradient plasticity. And this plasticity is based on the concept of elastic ranges. So we can use all the knowledge we assembled from elasticity again and put it into a wider range. And if I then have some time left, I will try to open the door to include thermodynamics. And as a climax, I plan the compatibility with the Clausius-Duhem inequality. Okay, let's not use and lose time for that. I always try to follow the very nice and clear and direct notation of Trussell and Noll, which is appropriate for classical materials, but when you go into gradient materials, have a lot to do with third-order tensors, and which normally not occur in mechanics, in classical mechanics, and you need some new notations to also write it down symbolically in a short writing. So I want to introduce two special products. One is a well-known Rayleigh product between a second-order tensor and a tensor of arbitrary order, and this is simply that you represent this tensor in such a form with respect to some basis, and then transform all the base vectors simultaneously by the second-order tensor. This is called Rayleigh product and indicated by this little star. And I need another product which you might interpret as a push forward or pull back operation on a specifically applied to a third order tensor A. So it's a second order tensor T and third order tensor A, and that means that in the last two entries we simply apply the T, and in the first entry T to the minus transpose. This has something to do that the last entries are vectors and the first one is co-vector, or vice versa. So there's a little difference. This is indicated by this little ring, or is it a bagel? Let's call it bagel product. It's a bagel product. Okay. The starting point is the stress power in the internal power. In classical continua, in Cauchy continua, it's just this term, and we add just one following term. Third order stress tensor being conjugate to the second gradient of the velocity. Now this is in space. We try to translate this into a material form, and the material form can be given here. This is well known. This is their second Breuer-Kirchhoff stress tensor, and this is the right Cauchy-Green tensor. But for the third order tensors, you have a couple of choices, and I tried a lot of them. Most end up in very, very lengthy formula. So you can use gradient of C, what Tupin did and many others tried. You can also use F transpose gradient F. We have infinitely many choices, but it turned out that this guy, F to the minus 1 times gradient F, is a good choice, is perhaps the most practical choice among all of them. Some people call this the connection, which might be confused with Nobler or something. Some people call it curvature tensor, which can also be confused with Riemann's curvature tensor, but it expresses the change of the curvature in the material. So it's perhaps not a bad. You might also call it a Hesse tensor because it contains the second derivative. So I will further on call this guy in connection with this one the configuration in the point of the material point. And you have a third order hybrid stress tensor which is conjugate to this one. Now, what are the properties of these tensors? C, of course, is positive, definite, and symmetric. All the third order tensors which appear here have the right subsymmetry, all of them. Yeah, that's basically all we have. Now, the field equations from the balance law, as usual, Cauchy first and second equation. Cauchy's first equation is enlarged by this term, while the balance of angular momentum does not affect the higher stress tensors and gives just second order tensor being symmetric. Okay. Now, let's start with elasticity. Second gradient elasticity. We assume that the second and third order stress tensors depend on the motion, on the gradient of the motion, and the second gradient of the motion. And then we have to confront this ansatz with Euclidean invariance principle, and then you get reduced forms. And the reduced forms are like that the second Piola-Kirchhoff stress tensor and this third order hyperstress tensor depend on the configuration, that means on C and K. And this is part of the configuration space. If you prefer a hyperelastic form, then you would assume that the specific work depends on the configuration. And if you plug this in to the stress power equation, you will find the usual potentials then. Well, the first one is usual, and the second one is the extension to second gradient materials. Now let's consider change of the reference placements. All these materials variables do depend on the reference placement. So what happens if we change the reference placement? We note A being the gradient of the change of the local gradient, second order gradient of the change of the reference placement. We all know that the deformation tensor is transformed like that, and then as a consequence the right Cauchy-Green tensor is transformed that way. But after a longer calculation you will find out that the third order configuration tensor consists then of two parts. One is a multiplicative application of this Bagel product to K, and you have an additive part, and the additive part is just the configuration change between the two. And then, because of work conjugacy, you get the transformation behavior for the stress tensors. Okay. If A is in a particular case just a rotation, then all these transformations become of a very simple form, because then the gradient of A is 0 and its determinant becomes 1, so you just have the Rayleigh product here, rotation of the two tensors. Okay, now we want to precisely express the notion that 2 points consisting of gradient elastic material do have the same behavior. Well, this can be the case when the two elastic laws are identical, but in some cases you have to first change the reference placement until you gain this easy criterion. So the definition goes, if you have two elastic points x and y, and you have the elastic law with the two, then we consider as these 2 points being isomorphic if you can change the reference placement in such a way that in the reference placement the density is equal, and second, the elastic laws with respect to these new reference placements also are identical. Now this is not very practical, this definition, so by standard arguments you can reduce it to the following: 2 points, 2 material points with elastic laws with respect to arbitrary reference placement are isomorphic if you can find 2 tensors, a second and a third order tensors, such that these 3 relations hold for all configuration. So instead of changing reference placements, we just try to find 2 tensors. That's much easier. And if you apply it to the energy of the 2 points, then it will result in such a form with some additive constant there. If we apply the isomorphic concept to the point itself, we get automorphism or symmetry transformation. I gave it another name. What was P before is now A to indicate this difference, but the mathematical concept behind that is the same. So if you have the elastic law for the two tensors, capital K and small k, depending on the configuration, then a symmetry transformation would be A from the outside, A transpose in the inside with a Rayleigh product, then A transpose with this Bagel product to the third order tensor plus an additional third order tensor. And if you apply to the symmetry transformation to the energy, you will end up with this form. And again, special cases are just rotations. In this case, this large A, this triple A is 0, and you have this much nicer, easier, shorter form. Now let's move to gradient elastoplasticity. The basic concepts for that is the concept of an elastic range. What is an elastic range? An elastic range is a region in the configurational space where the material behavior is elastic. Okay, so to make this more precise, this is the subset of the configurational space, and within them you have two elastic laws such that the stresses can be determined by these elastic laws as long as the process is within this particular elastic range. If it's on the boundary and tries to go outside, trespass the boundary, then yielding occurs. The material has to necessarily change the elastic range. And if we change the elastic range, we have to change this subset due to hardening or softening or anything. It might change its form and its size, but you also have to change the elastic laws. And the question is how the change of these elastic laws will take place. And here I use the same assumption which we used also for classical elastoplasticity, namely the assumption that the elastic behavior before and after yielding is the same. That means, in precise concepts, it's isomorphic. So we apply the isomorphic concept to that. This is a very strong assumption which some materials do fulfill and others don't. So in crystal plasticity it seems to be almost ideally fulfilled, whereas with changing texture, etc., it's more or less fulfilled. Now, if all elastic laws in different elastic ranges are mutually isomorphic, then you can choose one as a reference range, not a reference placement, a reference elastic range, and map all these to this one. This has the advantage that during yielding the function itself does not vary, but only a variable. And change, this is why we studied the isomorphism. So you introduce that way two tensors, a second order and a third order tensor, and the interpretation of that is not a deformation but a transformation. We call it plastic transformation, and this will be the basic plastic variables in this theory. So we have the elastic laws in the current elastic range, indicated by P, and they are transformed to two constant elastic laws which do not vary by means of these P's. What we need is a yield criterion in the configuration space, so we assume that the yield criterion depends on all variables which we have. That means the 2p, the configuration, plus additional hardening variables, which may be tensors of any order z. And the loading condition would then be that the partial derivative with respect to the configuration are positive. In the case when both conditions are fulfilled, then necessarily yielding has to occur. If you now consider the stress power again, plug this all into the stress power, then after a long calculation, you can find the following presentation of the stress power. You have a variation of the elastic reference energy, purely elastic part. Then you have dissipative parts which work on the change of the plastic variables P dot, here, here, and here. So this all breaks down. If yielding does not occur, then you have purely elastic ranges. Otherwise, you have these parts. Running out of time. So we need, for the internal variables, we need evolution equations which are called flow rules and hardening rules. We make a following ansatz with a positive plastic multiplier and times a function which more or less gives the direction of yielding. And this depends on all the variables which we have introduced, plus two variables which give just the direction, the normalized direction of the change of the configuration. That is, we divide the material time derivative by a common factor mu, which is simply the length of this guy and the length of this guy. And because of dimensional reasons, we have to put in here a factor of the dimension length square. And then we plug this into the yield condition as usual and get a consistency condition. We can solve that for lambda. So this is a classical procedure at that point. We come to the thermodynamical theory. I have to accelerate a little bit. So we need the specific internal energy, the heat supply, the heat flux, the temperature gradient, the entropy, and the free energy. And we have to enlarge the concept of elastic ranges to thermoelastic ranges. So we need a whole set of elastic equations for all these variables. And the thermoelastic set, this thermoelastic range is then a subset of the configuration and the temperature. Okay. We also apply this assumption that all the thermoelastic ranges are isomorphic. So we need the isomorphic condition for all these equations, for these thermoelastic equations. And what is important there is that we have certain constants here. Now, the isomorphic condition says that the thermoelastic behavior, as far as we can measure it, must be the same. That means the entropy cannot be measured. The free energy cannot be directly measured. What we can measure is the change of the internal energy because of the first law. And so the internal energy then can only be determined up to one constant. And if we do the Legendre transformation, then we get a decomposition, a natural decomposition of the free energy in two parts, what people sometimes call the elastic part and the plastic part. So the plastic part cannot depend on the current elastic variables. It is not allowed to depend on the configuration, the temperature, and the temperature gradient. But of course it can depend on all the plastic variables. And one should not neglect this fact. Now, the yield criterion depends on all these variables again. The loading condition is similar as the one before. We again have the evolution equation, namely the flow rule and the hardening rule. And again, we have to normalize these increments, but now we also have the temperature change in here, which is normed by a reference temperature. And now we plug this all into the Clausius-Dürm inequality. I'm not doing anything revolutionary with respect to the temperature, so it's classical thermodynamics, and we end up with the following necessary and sufficient conditions for the Clausius-Dürm equality to hold. The free energy does not depend on the temperature gradient, and the free energy is a potential for both stresses and for the entropy. We have the heat conduction inequality, and we have a residual dissipation inequality, which is a restriction to the flow rule, the hardening rule, and the yield criterion. Now the timekeeper outside rang the bell. I have to come to an end. So I skip the temperature changes. It's getting cold tonight. I skip the resume. I just go to the reference one, and we'll anxiously wait for your questions.
Simply wanted to know more details about your choice of K.
Yeah.
Because I also was fighting with this choice.
Yeah.
And I found more convenient grad C. So maybe you can tell me why you prefer.
Yeah. If you calculate, for example, grad C under change of reference placement, it becomes very large and complicated. But essentially, the particular choice of this variable is immaterial. So all theories are equivalent in that sense. It's just a matter of convenience. That's why I choose this one. And I tried grad C, but it was long calculation.
How do you define something like the elastic fluid?
Yeah, that has been already done by Cross and others. You just have to apply representation theorems. You know what the symmetry group is. It's a full unimodular group. The second order P is unimodular, and the third order P has a symmetry. Some people call it trace to be zero. If the Jacobian is constant, that means that gradient of J is zero. Okay, and gradient of J is dJ over dF. Times gradient of f. And derivative of the determinant to a tensor is j times f to the minus 1, and it's a double contraction here. It must be double contraction with gradient of f. Now j is constant, is 1, and this is k. So this is, some people call this trace of k, but it's a vectorial trace. It's in the first two indices. That has been found by Cross already in the 70s, and later by Murdoch and by Vianello and Podio-Guidugli and others. It's a simple, yeah. Okay.
No further questions before Francesco gives some further announcement. Let's say